Welcome to this fourth lesson in the second module of the course on Fundamentals of Computer Architecture. The topic of this lesson is Basic Code Optimizations. This lesson is slightly based on section 3.2 of the textbook by Hennessy and Patterson, but most of it has been developed by myself. To explain the basic code optimizations, I will use this code as a running example. We have an array X of 1000 doubles and a scalar value S. Then there is a for loop that adds the scalar S to each array element X or I. First, let's consider a straightforward translation to MIPS assembly. Here's the code again, and I will assume that register R1 contains the base address, the start address of X, and that register F1 contains the scalar value S. A straightforward translation to MIPS assembly looks like this. First, we initialize I with 0 and R4 with 1000. Then we compare I to 1000 and set R5 if it is true. If R5 equals 0, then we leave the for loop, jump to N4 and continue with the rest of the code. Otherwise, we shift I left with 3 bit positions because 8 times I is the offset in bytes in the array. Then we add this offset to the base address of array X, which is contained in register R1. So after this instruction, R5 contains the address of Xi. Then we load Xi into register F0, and then we add the scalar value S, which we assume to be in F1 to F0, and store the result of this addition in F0. Then we store Xi in memory. Register R5 still contains the address of Xi. And finally, we add 1 to I and jump back to the beginning of the for loop. We immediately see that in this straightforward translation there are 9 instructions per loop iteration and that we need 2 jumps per iteration, one at the beginning and one at the end, as highlighted here in blue. An obvious question is, would a single branch also be sufficient? By analyzing the code, the compiler found that the loop bound is 1000, which is a constant, and it will be iterated at least once. So we can move the branch to the end of the loop and eliminate the branch at the beginning. This optimization is not legal if the loop is not executed at least once. The code sequence is mostly similar. We initialize R3 containing the loop index I with 0 and R4 with 1000. Then we calculate the offset, add it to the base address and load Xi. Then we add the scalar S to F0 and store the result to the memory at address R5. And finally, we increment the loop index and test if it is still less than 1000. If it is, we branch back to the beginning of the for loop, otherwise we continue with the rest of the code. Now we have 8 instructions per loop. We have made a small improvement of 1 out of 9 instructions per iteration, but there is still scope for more improvement. As said, moving the branch to the end is valid only if the loop will be executed at least once. If not, it's not a legal optimization. If the loop bound is a variable n which can be less than 0, as highlighted here in red, 1 branch per iteration is still sufficient, but we need an extra test at the beginning, before the loop. This code with the variable upper bound n can be translated as shown here. Before we enter the loop test, we test if I is less than n as highlighted in red. If it's not, we do not enter the loop, but branch to the end of the for loop immediately. The rest of the code is identical to the code before. We still have 8 instructions per loop iteration with 1 extra test before the loop. It's still more efficient than the loop with 2 branches. What can we do more for this code? The second optimization I want to introduce is eliminating induction variables. Instead of recalculating the address of Xi in every iteration, we can start with the base address and add 8 every time so that it points to the next element. Here is the code after we apply this optimization. Instead of the shift left logical and the addition of the offset to the base address, we have a single add immediate that adds 8 to the address contained in R1 as highlighted here in red. Now we have 7 instructions per iteration. We started with 9. The question now is, can we get rid of the induction variable I completely? Hint, yes. Let us see how. In the previous implementation, I was still needed because we needed to compare I to the loop upper bound n. However, instead of comparing I to n, we can also compare the address of xi to the address of xn. xn doesn't exist, it's the first element after the array, but we can still compute its address. If the address of xi is larger than or equal to the address of xn, we leave the loop. Here's the code. First we compute the address of xn. If the address of x0 is larger than or equal to the address of xn, then we never enter the loop. Otherwise we load xi, add the scalar to it and store back the result to xi. Finally we add 8 to the address contained in R1 so that it now points to the next element, xi plus 1. Test if the address of xi plus 1 is less than or equal to the address of xn, and if it is, branch back to the beginning of the for loop. Beautiful! We started with 9 instructions per iteration, now we have only 6, a 1/3 improvement. However, only 3 of these instructions are really useful: the load double, the add double and the store double. These 3 are necessary whatever tricks we apply. The other 3 instructions, the update of the address register, the set less than and the branch, are loop overhead. We can reduce this overhead by applying a technique called loop unrolling. Loop unrolling makes several copies of the loop body and therefore the unrolled loop needs fewer iterations than the original loop. It is best explained using a code example. Here's the original loop that iterates 1,000 times, and here's an unrolled loop unrolled 4 times. In other words, the loop unrolling factor is 4. 4 copies of the original loop body have been made, and after each iteration the loop index I is incremented by 4 instead of 1 as highlighted in red. Here I show the assembly code after loop unrolling. It is very similar to the code shown before, therefore I will not discuss it in detail. Notice, however, that the offsets in the loads and stores need to be adjusted in order to load and compute the correct elements, as indicated again by a red font. Furthermore, the address contained in register R1 needs to be incremented by 32 instead of 8. Now we need 15 instructions to process 4 elements. In other words, we need 3.75 instructions per element. Our original code required 9 instructions per element, so we have reduced the number of instructions by a factor of 2.4. As explained in a previous lesson, however, instructions are not cycles. Another advantage of loop unrolling, besides reducing loop overhead, is that it allows instructions to be rescheduled. More about that in the next lesson. In the general case, the loop upper bound n may be unknown at compile time, and it is not necessarily a multiple of the loop unrolling factor k. In this case, we need 2 loops to replace the original loop. One that is unrolled and iterates n divided by k times. Here integer division should be applied, which implies that n divided by k should be rounded down as indicated here by using the floor operation. And we need a loop that is a copy of the original loop and that iterates n modulo k times. However, modulo as well as division is an expensive operation that should and can be avoided. This example shows how our loop can be unrolled if the loop upper bound is a variable n. The first loop is unrolled and its test has been replaced by the test I plus 3 less than n as highlighted in red, since I plus 3 is the last element computed in the iteration with index I. The second loop is a copy of the original and has an empty initialization statement. It simply continues where the previous loop left off. Finally, an exercise about loop unrolling. Consider the code shown here, which computes the dot product of 2 arrays aka factors a and b. The compiler has generated this assembly code. The exercise is to first add a short CLI comment to each line of assembly code. In particular, this comment should explain what is contained in register R9. Second, to unroll the C loop 3 times, and finally, to unroll the assembly loop twice. I strongly recommend you to do this exercise in order to have a better understanding of this important optimization technique, loop unrolling. This completes this video. Thank you for watching. In the next lesson, I will start a new module about pipelining. Hope to see you back.